The gas laws. We're now going to look at the relationships between the four properties of a gas, which we showed already. Okay, we have pressure, temperature, volume, and number of moles. For an example, Robert Boyle in 1662, quite a ways back, studied the relationship between pressure and volume of gases, and he kept the other two variables constant, the temperature and the number of moles. Boyles Law is the relationship between pressure and volume of a gas. We'll also study three other laws that examine the relationship between pairs of variables, and then we're going to put them all into one law. There are four gas laws, and what they do is they show the relationship between two of the four properties of a gas under varying conditions, and you keep the other two variables constant. As we just alluded to in the previous slide, these four laws were eventually combined to create the ideal gas law. Physicists and chemists like doing that, getting to as few laws as possible. So we start with Boyle's law, that takes care of pressure and volume. Charles's law relates volume and temperature. Avogadro's law, volume and number of moles. And finally, Gay-Lussac's law, which is pressure and temperature. Let's examine Boyle's law first, which deals with pressure and volume. And remember, we have to keep the other two variables constant. So that's what you see here. Temperature is constant and the fixed number of moles of the gas. So if you increase the volume of a container, gas molecules will collide less often with the container, which will result in a proportional drop in pressure. Kind of makes sense. There's more room for all these particles to move around without hitting the walls. This is an inverse relationship. Inverse means that pressure is 1 over the volume. You increase the volume, you decrease the pressure. Another way of showing that, instead of with the proportional sign here, that's what that alpha means, you come up with a constant, we'll just call it K, K for constant. So V equals some constant times 1 over the pressure. So let's see over here on the left, we have a volume of 2 liters, and we find that the pressure is 32 millimeters of mercury. When we expand to 4 liters, we note the volume was doubled and the pressure got cut in half. That's an inverse relationship. It went down to 16 millimeters of mercury. So in the beginning, more collisions, higher pressure. At the end, fewer collisions, lower pressure. The inverse relationship between pressure and volume is known as Boyle's law. So volume is some constant times 1 over pressure. We then have a plot here. We have pressure on the y-axis, volume on the x. So as the volume increases, the pressure decreases. And if you halve the pressure, the volume is doubled. And you can check out the data on the previous slide, slide 52, and this must be Boyle. Graphs like the one on the previous page are hard to figure out. We don't like curves, we like straight lines. The trick there is we're going to plot volume against 1 over the pressure. And if we do that, look at this, that's just y equals mx. So if this gives us a straight line, the slope here, what's that going to give us? That's going to give us the value of k, the proportionality constant. Here's volume, that's cool. Instead of pressure, we plot 1 over the pressure. We now get this straight line, and the slope of that is k. This is a great trick. You can use it all the time when you're graphing quantities like that. Here's a little simulation you can do. And first, let's give credit to the person who came up with it. And that's right down there, Professor Tom Greenbow at Iowa State University. And what you do is you use the mouse, or if you have a touchscreen, your finger or a pen, to drag the plunger to your desired volume. Data will be automatically recorded in the table over here when you release the mouse. Now this might not work with future versions of Adobe, but hopefully it works now. So let's see here. All right. So look at how the pressure is increasing, and then it comes back down, it decreases when the volume expands. We get some data there. Oh, I see. It waits till you get to there and then it records it. Okay, and let's see if we can get a graph out of this. Hey, pretty cool. And then you can connect the lines. And notice this is graphing pressure versus volume, so you will get that curve. You won't get a straight line. It'd be much cooler to graph 1 over the pressure or 1 over the volume to get a straight line.